our second year, so we're not quite a veteran yet, but we try to become one. As Kai pointed out, Rohde Schwarz testing, so we're a company that do test measurement solutions since, well, 75 years plus, I would say. My specialty is more the wireless side, so I'm working on LTE and LTE Advanced, so you may think, why the guy is talking about video, but I'm glad that we can another time support the agenda of the Texas Wireless Summit with 2 demos that we have outside. So one is of course on video, so I encourage you to see that. The other one is probably the most expensive video race game that you can think of. So who's following NASCAR? Nobody? Okay, so we will pack it. So, I mean, if you have seen Indy 500 or so, you can race that race outside before to it. So it's very interesting. I encourage you to spend a moment on that. With that, I just want to go ahead and talk, and I'm glad that nobody of the previous speakers already used the slide that I prepared. So thanks to our colleagues from Cisco for doing all that work and you know, trying to measure the expected or predicted explosion in mobile data traffic. I stole a slide from them, but there's the source, so thank you for that. As you can see, already in 2012, we reached 1.3 exabyte of mobile data traffic per month, right? So the first time I read exabyte, I was thinking like, what the heck is an exabyte, right? So it's a billion bytes, and even that is not really an example. So if you think about that, and your favorite movie on a Blu-ray, Avatar, Dark Knight, whatever your preference is, that's about 26 million Blu-rays that are transferred each and every month wirelessly. So that's quite some data that goes over a wireless link. And to do that in the right way and keep latency and high data rate per user in mind, we do that with LTE, obviously. So in order to support that further, when we're looking at who's responsible for that traffic, it's video, right? So we use that, everybody uses that as an excuse to work on video, and we use it as an excuse to do some more test and measurement equipment. You see that here in 2016, it should reach like 2/3 of the volume, so almost 70% for that. And that's of course something that we need to take care of and make sure that from a user experience, that means if you or me are using our smartphones to watch a video, that the video is transmitted reliably and that my device is able to handle that with all the things that may happen to the transmission and decoding or decoding process. So I don't want to break another tradition. If you have a technical talk, you have one slide that shows data explosion, you have another slide that shows network architecture, so here's my one. It's a simplified one to show you like the LTE architecture with all the network nodes that we have to realize that flat, all IP-based architecture here with the serving gateway, the packet gateway, the MME controlling the mobility to the base station, what we call E-node B, right? And then our LTE devices. And what we try, of course, sometimes we try to access, you know, YouTube, watch a video, or Netflix, or all these other services that are out there. And basically, what happens is basically this video transmission, if it is peer-to-peer, for instance, is impacted by a number of things. Basically, 2 things: the things that you face on the air interface, so my multi-path propagation, noise, fading, all these kind of things impacting the transmission from the tower to the device. And the other part is, of course, what happened to the core network, as it is an all IP-based network. There is, of course, the impact with IP impairments, jitter, delay, packet loss, corruption, all these kind of things. So these are the things that are impacting my transmission, and of course, the video quality and the perception of the user. And you know, we're looking a little bit in the future. This is release 8, there's release 9 coming, that offers multi-pass or broadcast capabilities in LTE, known as involved MBMS. And there's more elements coming. Of course, these elements are also impacted, for instance, by IP impairments. So before we coming into modeling that and how we can test that, I just want to talk a little bit about that. And there's probably more experts in the room here than I can talk about it. What is video quality? Basically, it's dependent on you and me, right? It's a degradation of the video compared to an idle reference. For instance, that's an example. So we're using a reference file to compare it to the video file that we're seeing. And there's 2 ways to do that, basically. It's subjective and objective. subjective means we take a bunch of guys like all of you here in the room, I show you a video and each and everybody says, okay, that's good, that's excellent, that's fair, and how I see it and how you see it, that may be totally different. So this is a subjective method. What we try to do is we try to get to a mean opinion score that basically tells us how good or bad the quality of that video file in that example is. And then there's the objective way where we're trying to model that and put that into a context and make it repeatable and automated and accurate and use it for measurement purposes. And there are two measures that are having been defined to do that, to adopt these mean opinion score. That's one is the PSNR, peak signal to noise ratio, and the other one is SSIM, so structural similarity. And these are two things that have been integrated into our video tester or the video tester family that we are using to judge video quality. The structural similarity is a little bit better to judge the mean opinion score that you normally get when you take a bunch of guys watching a video. The reason being behind it is it works better with how the human brain works, right? So PSNR compares frame to frame and tries to identify errors, but our brain works a little bit different, so we try to watch patterns, and that's what structural similarity tries to simulate. So these are the two measures, and if we're looking into video processing chain, there's a couple of things that are impacting that process. You have the encoding of the raw video data on the one side, and for video over wireless, as I would call it here, and not specifically just LTE, you probably take an MP4 container and put a video encoded file in it, and then an audio encoded file, and using these different types of codecs that are available there. And then all these things that happen need to be taken care of. You need to make sure, when you're encoding, audio video delay is not there, and you don't violate buffer rules, things like that. And each of these steps in the processing chain are owned by either the content provider, if we're talking about the link where we transmit it over, in LTE of course wirelessly, that's the network operator, right? So having a good network there. And then on the other side you have the handset manufacturer that receives that video and needs to extract it from the LTE link, and then of course put it in a decoder and display it on the screen. So if we access something on YouTube, we normally don't have any chance to work on the encoding process because the video is already there. But what we could do is in the lab, in testing devices and simulate what our network has an impact to, is we can help the operators to do that, and we can help handset manufacturers to optimize their devices for video transmission. So how are we going to do that? So first of all, what we need is a base station emulator, right? So something that emulates an LTE or 3G or 2G network. On our end, that's called CMW500. That's what you see on the bottom here, the nice little box that is also outside use. So I would set up an LTE cell where my device registers to, gets attached to, I can set up a connection and start transmitting data. On the other hand, for fading purposes, I would use a fading simulator, right? So this linked to my base station emulator. We even have the capabilities to do the fading internally in the box, but that's not as flexible as with a own box. And then, of course, you have some software that's going to be used to control it, to set up everything and make it easy to use that kind of setup. So we call it PQA, Performance Quality Analysis. It's basically used by various operators worldwide. One is here in Austin. To judge the performance of devices for data throughput and these kind of things here. What we do now, we extend that and add another box, so it's a box business, as you can tell, with a little tiny guy that we call a VTE, it's a video tester. And what it basically does is it interfaces to the device via an MHL, so that's the mobile high definition link. It's basically converting your micro USB connector on the device to a HD connector. Right? So you can connect your device to an HD TV and play your video file on the phone, and it will be displayed on that TV. Our phones have HDMI connectors, right? So it's, of course, as usual, there are multiple ways to do that. The setup that we have outside is using MHL at this point with one of these highly advertised devices, the Samsung Galaxy S3. So what we do is we set up the connection, we stream a video file that we have time encoded to use it as a reference, and we stream it over the link that's conducted at this point to the device and record the device with the video tester. So you have the chance to stream the device, to record the device, and use that as a reference on the test set. And then you can start to degrade your video transmission by adding fading, by adding IP impairments, and see what's going to happen. So you can add the IP impairments to emulate what happened in the core network, jitter delay, packet loss, things like that, and see how your device handles the video transmission. You can add then the fading and see, okay, what is my RF circuit in my device, is that good enough to deal with all that? And then, of course, you can put it together and see what the overall performance is. And that will help you then, of course, to judge how good the device is in handling that video file. So basically what we see is you have, I hope you can see that, otherwise I encourage you to go outside. So basically you have a measurement screen that performs all these measurement PSNR structure similarity, and what we do in the same graph is on the left-hand side you have the streamed video, on the right-hand side you have the reference file that we recorded, and the red one is basically the picture difference that you have, right? So if you add the IP impairments, the noise and such, you would see it gets really red, and if it is not impacted and it's still stable, then of course it will not become. So these are the kinds of measurements that you can take on your video transmission, and where we try to model what happened in the real network, in the real world, into the lab, and that will help carry us to characterize devices from a user experience point of view, right? Because at the end of the day, if I take my grandma and she wants to access a YouTube file, she doesn't care if it's 3G or LTE, she wants to watch that video from her grandson running around in Dallas while she's in Germany. Right? So that's basically what we really do. And she cares that the video is displayed correctly, and that's what we're trying to help them. Okay, so an example, just to visualize here a little bit the characterization of the device. What we did is, okay, we took a 2 megabit per second video that's encoded using the H.264 codec. We set up a link 10 megahertz, an LTE link 10 megahertz, 50 resource blocks. We used 23 resource blocks, so half the bandwidth, with a 64 core modulation, so one of the highest, or the highest possible modulation scheme in LTE, and streamed over that link these video files. So the maximum data rate, I hope you can see it, it's a little bit gray, that we can achieve over that radio link is 18 megabits per second. Yeah, if we did that, because we cover the peak data rates that the video would probably have. And what we have basically is a threshold that you can see on the bottom of 2 megabits per second. And if we violate that threshold, that means we have a lower data rate, of course, and we will start seeing picture failures, or video will stop hold basically, and things like that. So you have the SNR all plotted on the x-axis, you have the channel capacity or throughput on the y-axis here, and the dark blue curve on the very left is basically my curve without any impairments. So what we did then is we did add some fading profiles that have been specified by 3GPP, so vehicular and pedestrian, as you can see here. And then we plotted two curves, and what you basically see to cover up the fading, we need to get a better SNR to maintain the higher throughput. So what we would expect now, okay, picture failures still happens only if we now violate the threshold of 2 megabits. And what we basically saw is, when we set up that connection, well, picture failures happen much earlier than we would expect that, right? So what we can take away from here is basically, even if I have a high data throughput that's better than what my video needs, fading is unpredictable to a video transmission, right? Or nearly unpredictable, let's say that. So that means my picture failures, as you can see here with this little circles that you can see, happen much earlier, even if I have a really good throughput for that video to transmit like 4 or even 10 megabits per second, right? So this is something that only will be different if I use a different device. So if I have manufacturer A, that may look like this. If I have a manufacturer B in the exact same conditions, it may look totally different. Picture failure may happen earlier, may happen later. It depends, of course, on the implementation, on the video processing and such processors that are, and the encoding or decoding algorithms that are being used. So in summary, we can basically say that, okay, high channel throughput, high data rates doesn't guarantee a high-end, excellent video quality, right? Noise is something that we can handle, that's very predictable, and has a linear dependency on the video quality, but fading is really more or less unpredictable, right? So that means even if I increase my throughput and say like, why the heck is that video not streaming, right? The fading is the reason for, and it doesn't mean, okay, if we enlarge the bandwidth and high the throughput that we will solve that problem that we are seeing. Good, so to stick to my time, the slide showed in the beginning, video is important, right? The user experience is key, right? To me and you and all the other guys that are not working in wireless, but using all the devices, and high throughput really doesn't guarantee excellent video transmission. And who has enough of slides can come outside and I'll give you a little demo. And I saw already some people that did that and were very impressed. So come and see us outside. And with that, I just say thank you for your time, and I hope you have a great time. Back to Kyle.
Thank you, Andreas. The next part of the agenda is our first panel. We have Dr. Jeff Andrews, who you've heard from earlier, my co-host for the event, going to be